Today's topic is the motion of a rigid body rotating about a fixed axis. This is how the author starts. Some objects such as a brick or a thick steel rod are so difficult to deform that their shapes are virtually unchangeable, which is a simple fact from ordinary life. And we model such an object by a rigid body, which you know as a collection of particles forming a perfectly rigid framework. And any motion of the rigid body must maintain this framework. So for example, if a rigid body is moved in such a way that it's being stretched or compressed, then that's not a motion of a rigid body. Among the many different types of possible rigid body motions, an important type is rotation about a fixed axis. For example, a propeller which is rotating, or say a ceiling fan which is rotating, or a door which is rotating on its hinges, these are examples of such a motion. Let B be a rigid body, this body, which is constrained to rotate about a fixed axis OZ. The drawing is not a very good drawing of a rigid body which is supposed to be a three-dimensional object, but you get the basic idea. It can only rotate about this fixed axis like this. And in this type of motion, the particles of the rigid body that lie on the axis of rotation are fixed. Everything else is changing position. Rotation about OZ is then the only motion of the rigid body B consistent with rigidity. What the author really means by this line is that if you look at a single particle of the rigid body, that particle cannot move this way or that way. It is constrained to rotate about that same axis of rotation in a circle, and the axis passes through the center of the circle and is perpendicular to the plane of the circle. Now when there is rotation involved, the thing that you should measure is the angle of rotation. Let theta be the angular displacement of the rigid body B, which is this angle of rotation, at time t measured from some reference position. Say this is the reference position and this is where the body is at a general time instant t, and it rotated by an angle theta. In rectilinear motion, where the motion happens along a straight line, we have linear displacement x. If you remember, we discussed it back then. So this theta is the rotational version of that linear displacement. This one is angular displacement. Now just like we have linear velocity or ordinary velocity in rectilinear motion, or in general I mean, here we have this definition of angular velocity. For this rigid body, the angular velocity omega is defined to be the rate of change of that angle theta with respect to time, or which is just your theta dot. And the absolute value of omega is defined to be the angular speed of the rigid body B. Note carefully that both these quantities are scalars, and the standard unit for both of them is radians per second. Next we have this example 2.8, which actually is, there is nothing to do, you just have to convert units. The crankshaft of a motorcycle engine is spinning at 6,000 revolutions per minute. We have to say what the angular speed is in SI units. SI units means in radians per second. And the answer obviously is this. One complete revolution equals 2 pi radians, that you already know, 360 degrees. Here it's not given in degrees but number of revolutions. So 6,000 such revolutions means 6,000 times 2 pi radians. But it's given in per minute, which you have to convert into seconds. So that's why you divide by 60. I leave the simplification of this to you, radian per second of course. Next up we have particle velocities in a rotating rigid body. So if a rigid body is undergoing that type of rotation about a fixed axis, then in such a motion, each particle P of B moves in a circle of fixed radius rho, which of course changes depending on the location of the particle, and that radius is nothing but the distance of P from the axis of rotation. So here we are talking about general circular motion of a particle about a point. So the circumferential velocity of P is V equal to rho theta dot. We already know this from general circular motion. So that is rho times omega, angular velocity. Next we have example 2.9. In the crankshaft example above, that means example 2.8, find the speed of a particle of the crankshaft that is at a distance of 5 cm from the axis of rotation. And also we have to find the magnitude of its acceleration. Speed is the absolute value of velocity. That means the absolute value of rho times the absolute value of omega. Rho is the distance of the particle from the axis of rotation, that is 5 cm, or if we convert into meter, 5 divided by 100 meter. And this value, if you go back to the previous example and do the simplification, the numerical value becomes 200 pi. So this is your speed, 10 pi meter per second. Now next we have to find the magnitude of acceleration, and for that let's first recall this general acceleration formula. Acceleration formula for general circular motion, minus v square divided by rho times r hat plus v dot times theta hat. V is the circumferential velocity and rho is the radius of the circle in which the motion is happening. Now because this is constant, it does not change with time. So v is also constant, so that means the time derivative of v will be 0. So this term will not be there, it will vanish. So the magnitude of A will just be v square divided by rho. The minus sign will vanish because we are taking magnitude, and this is unit vector, meter per second square. Now I want you to put the values of v and rho and find the numerical value yourself. Let's end the video here. In the next mechanics video, we are going to see planar motion of a rigid body. For example, this marker is a rigid body. The type of motion that we saw today is like this, rotation about a fixed axis. But in that video, we are going to see what happens if, say, a rigid body rotates in some way, but at the same time it slides in a plane. Two types of motion are simultaneously happening. How can we describe such a motion?